Okay, good morning once again. So today we'll be talking about the relational model. But to remind you, for those of you who wanted to listen to the recordings from the past sessions, you can go to here, online meetings. And then in online meetings, you click on the I, the information here. And once you click on the I, you'll be able to play different files, like file with screen with speaker view, audio only, timeline, or audio script transcript. You will definitely need the password, which is right here. So you can just click or copy the password, and then once you click on the file, it will ask you for the password. You enter the password here, and then you would be able to listen to the recordings. Now, but for the first time, I actually, oops, sorry, record. Let me see. For the first class, I actually did the recording twice. So mainly you have like many things here. You click on the last one because it would say like from 9/11 to 12. 9/11 is not good number. But the first one I only did like 1 minute, so you can discard it and then take a look at the longer ones there. All right. So you know where to obtain the recordings from the past classes. And now let's begin with this one because there are a lot of content and I'm afraid that I can't finish it in time. Okay. So last week, we talked about the ER diagram, like from situation, how we translate from the information that we retrieve from each of the project, and then we draw an ER diagram. So for ER diagram, most of the things that you must be familiar with is that the entity, right? The name is entity and relationship. So you have to really grab what the entities might be for your own project. And then what the entities, you will have the relationship with links, which links between two or more entities. And then what you would do is then you would list all the attributes within each of the entity, if you remember that, right? So now we are going to take the ER diagram as an input, and then what we will have at the end of this session is the relation that will be ready to use within the database itself. All right. Now, so the chapter outline for today, I will cover the relational model concepts, the constraints and the database schemas, the some of the operations that you need to understand whether or not it would we allow how to take care of these within the database, and the relational database design, relational mapping, like when you have the ER diagram, how would you map to relational model? All right. So again, I already showed this the other day in the first class. I believe that the reason that we are still working on relational model, because the relational model is still one of the most popular. So if you take a look again, you will see that the first five, at least the first four, actually first four are relational models by nature. So they are Oracle, MySQL, Microsoft SQL Server, or Postgres. See, the top four, according to DB-Engine's ranking, are still relational. However, there are multi-models, within each of these products as well, because they grow from being relational by design, originally that they were born from. But right now, most of the database in the relational also include multi-model capabilities. However, you probably see still really just relational, like Snowflake. You can see that it's relational only, or here SQLite, relational only, Microsoft Access, Apache Hive, you can still see Google BigQuery is just relational. So that is the reason why we still need to learn about relational model, not only the NoSQL. So we will cover NoSQL for sure, but for now, we are going to focus on relational model first. So the concept of relational model actually, again, was proposed in, since 1970. I can't really think of any other computer technology that is that old and still being used today. So basically it was introduced like 50 years ago. more than 50 years ago. And if you are interested in learning more, you can read this paper that I listed here. And the concept that Professor Cott offer there is called the relational model, of course. And the behind the scene, the relation of the is the concept that he used. So he looked at the relational model is the data that is based on the concept of relation. But where does relation comes from? Basically, the relation concept is actually the ideas of sets. All right. So when we are operating the whole database, it's actually theory plus a little bit more. Right. Now, come to the relational database definitions, what we need to know. So when we look at the relational database, it's actually a set of relations. But when I talk about a relation, let's see what relation means. When we look at a relation, you can see the figure down there. So basically, you can see that a relation is just a table, right? If we take a look, it's just a table of columns and rows. Now, but there are specific ways that the database is treated and how they are computed, all right? So the terms or the definition that we will be using for relational database are these. When we talk about a relations, it actually is a whole table, all right? It's a whole table. Now, when we look at the table, we'll look at two different aspects. One is called a schema of the table or schema of a relation. When we talk about a schema, it's actually the structure of how the database looks like or how this table looks like. And then on the other hand, we'll take a look at the data in it. So the data in it will be called instance, all right? So the schema is actually how it is constructed, the structure of the relation or structure of the table, while the instance is the data at one point, is a snapshot of the data. So where the definition of schema would say that it specifies the structure. So what would be included in the structure? For example, the name of the relations would be within the schema, name of the attributes. For example, in here you see student ID, you see name, whatsoever here. And then you can say the type of the attributes as like string, integer, real. So these examples are whatever we talk about in the schema. So at the beginning, when the database is created, I mean, each of the relation or each of the table is created, you don't have any data within it. So when you created it, you create this, you called it a schema. So you know the structure of what kind of attributes are in there, the type of each of the attributes, but you don't actually have the data within it yet, all right? So now, once you have the data in it, you will have the instance. So if I talk about the instance, it's actually the rows and the columns, row and columns of the data within the table. And there are specific terms that we use in the database, relational database. So number of rows that we have, we'll call it cardinality. And number of fields or number of attributes, we'll call it degree or arity. So for each of the row, I say here that it has to have a key value of the data or set of items that uniquely identifies that row in the table. What it means is that for each of the row, you cannot have any duplicate. There is no duplicate. All right. Each of the row has no duplicate. So if I translate that, when we are talking about a relation, we talk about the schema or the structure of it first. And then when you have data within it, then we talk about the instance. Now, so I lay out how it looks like here. You can see that this figure shows the example of a relation named student, right? I'll write student here. Let me get the annotate. Okay, you can see that relation name is student, right? Now, for the relation name student, within the schema, we'll say that, well, we'll have the attribute called student ID, name, registered counselor number, and region. So these are just the example of the attributes within a relation called student. All right. Now, aside from the name of the attributes, the structure would also say that student ID is probably a string of 3 here for the example here. Name is string of how many characters you can name it. Registered, you can say that, oh, this is probably the year, so it would be uh integer of 4 and 4-digit integer. So counselor number, you can also have like numeral 4 or maybe it's like 4 character, and region is like some kind of number with like just one numeral. All right. Now, so for the schema, okay, again, I'll just now use the terminology for database. So database would call a table a schema. So when you talk about schema, it's just a table, all right? But within the schema, you have to have relation name. The whole thing, the table is called a relation, and the name here is student, all right? Now, for the instance, you have row and column, and here, each row will call it a tuple. Some will read it out as tuple or tuple. I hear it both ways, so it's fine. You can call anything tuple or tuple is fine. Now, for tuple, one line or one row is called a tuple or a tuple, right? And then if you have many rows, we will say that for this particular relation, there are how many? There are 6 rows, right? So for this one, we will say that this relation called student, this relation called student has a row of 6. So we say that the cardinality of this relation is 6. All right. So cardinality is simply the number of rows. However, we also talk about number of attributes or number of columns or number of fields. We'll call it degree. So right here we have 5 different items or 5 different columns or 5 different attributes. So we say that for these relation, the degree is 5. All right. Rows is number, the cardinality is number of rows, and degree is number of attributes. All right. Now you can see that each of the row will have some unique number that identifies it, such that no 2 rows would duplicate. So in this particular example, student ID is a key, which is unique for this whole table. All right. So you probably have student ID number 11 with the same name, same registration year, and so, but the student ID cannot duplicate. So this is the example of what a key is. All right. Now, another thing that I need to talk about for the structure or the relation schema is that each of the attributes must have domain. All right. So what does domain means? Domain means that it's a particular characteristic that each of the attributes must obey. For example, I could say that domain of names is a set of strings less than 50 characters because, somebody might have very, very long name. So I said set of string less than 50 characters that represent first name of person. So it means that whenever you call it name, the domain must be like every data in the attribute called name must be string. For example, broadband and David would be name. So if you have like Harper 7 and you have number 7 there, would that still be in the domain of name? You can, right? Because if you treat the number as character, so that's fine. Now, for the citizen ID, the example of domain would say this. It's a set of valid 13-digit ID given by the government. So I say that at least it has to be 13-digit ID. But now for the domain, you can also have this specific constraint that the data must be valid. For example, if you know that the last digit is a check digit, then you have to compute that check digit such that it is valid within that domain. So, example of this like 13-digit ID is like this. Now, the domain of the GPA, I would say that it is a possible values of computed grade point average. Each must be real, a floating point number between 0 to 4. So it could be 4.00, it could be 0.00, but every data within the GPA column or GPA attribute must act the same way. All right. For age, I say that it's a possible ages of student computed from date of birth. Each must be an integer value between 15 and 100. So it means that I would only allow number 15 to 100 to be kept within the database. If it's less than 15 or over 100, I will reject it, or this database will reject it as invalid age in this particular domain. But you can design the age within your systems differently, right? For example, for for the government of each of the country, you have the citizen registrar. In that case, you would allow from 0, right? The age, the domain of the age could be 0 to anything. So you could probably set and how do I say, set a limit to like 200, because nobody is aged more than 200 anyway. So it could be like 0 to 200. So the domain is something you specify on how that attribute should act, how that attribute should be validated before it is computed and or computed or entered into the database. All right. For example, phone number, how many digits, such as something like that. So if you enter just like 4 numbers, then it wouldn't be accepted by the database, or it means that the domain is violated, right? Now, here is the, again, I bring out that example again to summarize the definitions here. Informally, we call a table, right? We look at the figure on the left, we call, oh, this is a table. But in the database, we call it relation. And when we take a look at the column header, in database, we call it attribute. Okay. Each of the row, we call it a tuple or a tuple. Okay. The table definition, like how many attributes are there, how many rows, we call it schema of a relation. So it's a definition, we call it schema. If the table is populated, we have a state of the relation, meaning that you have the instance within the table. And for all possible column values is the domain of the database. All right. So these are the formal terms that we'll be using in relational concept. Right. For formal definition, we can also say, when we write it mathematically, we can say that we have a relation R with attribute from A1, A2 to AN. So R is called name of this relation. So you can just replace R with the name of the relation. For example, the relation student that we had before, R would be replaced with student. And A1 to AN would be the name of the attributes that you have in the systems or in your design. So we say that a relation schema R is defined over attributes A1, A2 to AN. And each attribute AI, for example, A1, A2, each AI is the name of the role played by some domain D, such as like string or integer or string of 50 characters or something like that in the relational schema R. So D is called the domain of AI and is denoted by DOM AI here. So the degree or arity of a relation is a number of attributes and of its relation schema. So basically, these formal definitions and the previous one right here is exactly the same, but you can write it out as a schema way, or you can write it out with the mathematical notations here. Right. Now, we'll talk about the characteristic of relation. So usually when you have data within the relation, all right, data within the relations, each of the row will call tuple, right? Okay. So what we say here is that the ordering of the tuple in the relation are, right? These tuples, each of these tuples are not considered to be ordered, all right? So basically, when you have a database and you populate data in it, if you don't set anything at all, it would be appended at the end, all right? the new information or the new data that you entered in the database will be appended at the end of the table, right? So we do not consider it as an ordered file, right? Although it is appeared in the tabular form. Yeah. Now, what about the attribute? In the attribute, on the attribute side, it's different because for the attribute in a relation, we will consider attribute and the values of it to be ordered. It means that when you have the attribute, like, let me show you here. You have the attributes here, right? Student ID, name, registered counselor number, and region. The attribute must be ordered such that when you have the new row or the new tuple, the data within the tuple will have to be ordered according to the attributes. So again, there are two things. If you look at each of the tuple, generally, they don't have to be ordered because once you enter new data, it will be appended at the end of the table. Now, but for the attributes, it must be ordered such that when you enter the data, it will be ordered according to the attributes, all right? Okay. So that's why I'm saying here that we will consider the attributes in R, in the table, called R, AN to A1 to AN, and the values in it. So here you see that it's a tuple with value V1, V2, Vn to be ordered because it has to be ordered that way, okay? However, it says that a more general alternative definition of relation does not really require this ordering, but mainly we consider it to be ordered, all right? Now, the values within the tuple, all values are considered what we call now atomic. When we say atomic, it is indivisible, meaning that you have the data that cannot be divided anymore. For example, if you have name comprised of first name and last name, then you can divide between first name and last name. But within the database, each of the data, or each of the value in the tuple will not be indivisible. So we call that it is atomic, all right? Now, if you do not have any data within each of the column, in any of the column, then we patch what we call null values. And so when we have null value in it, it means unknown or inapplicable. It is very much different from space, or zero or dash, because, if you have space, the value is space. If you have dash, the value in the database is a dash. Or if you have zero, of course, the value is zero. But if you don't know the value or you can't find the value to be input in the database, you will replace the information as null, right? There are some funny stories as well. Some people have their car registration, in some of the countries, you can design, whatever name you want to put on your car registration. And that car registration, somebody put null on their car registration plate. Okay, what happened is that when it was a catastrophe, it was like a mess because when that car was they violate something and they got fined from the government, from some of the like transportation department. What happened is that there was a lot of complication to compute the fine, so that person named null. And in the world, there are people actually with the last name null. So in the database, it's like such a mess when you have to compute that thing. It was a lot of story. You can search the problem on null, on Google, and you can read it out, or I can give it to you the next time. It was a lot of fun. All right. So here, the notation are, okay, when we say relation R with attribute number 1, attribute number 2 to attribute number n is a relation schema R of degree n. So when we say of degree, you remember, right? Degree is what? The number of tuples or the number of attributes? Which one? Who say number of tuples is the degree? Number of attributes? Okay, all right. Okay, now we refer to the component values by tuple T. So here you can see that when we represent mathematically, I can say that T or tuple of AI. So it means that we are looking at particular tuple and particular attribute. So now you can identify each of the cell within the table. Or you can use this way to signify it as well. So you can write either T and bracket AI in the middle, or you can use T dot AI. So this is the value of, particular tuple for that particular attribute. So similarly, you can say that if you have a tuple with value of AU, AV to AW, it will refer to the subtuple, right? Subtuple means that you have a tuple, but you only refer to part of the tuple, right? That contains a value that you look for. So this is how you will write it formally with mathematical notations. Here is another example. So if I say, I can say either way. I can say T3 dot H. Okay, this is a dot notation, or I can do the bracket T1 bracket H. It means the same thing, that I'm looking for tuple number 3 with the attribute called H, and then you can retrieve the value from that particular cell. So T3 here is a tuple number 3, which is Charles Cooper here, and age is 28. That's why you get the result of 28 here. But T1.H would be, T1 is Dick Davidson, and his age is 25. At the same time, you can say, I'm looking at T5, and now this is a subtuple. So when I'm looking at T5, I want SSN, name, and GPA. That's why you retrieve the data here. This is his SSN, name, and GPA of tuple number 5, all right, which is Benjamin Bear. Okay. Now, when we are talking about the database that you look at, we look at the table, and we have the data within the table. However, what we really want to do in the table is that we want to have the correct information, and we don't want the duplication. We don't want any redundancy, or at least minimize redundancy, minimize those errors, such that the database that you have contain the data that is credible, right? Now, within the relational database, there are constraints that can help you validate the information or the data that you look for. And here there are 3 different constraints first. The first set of constraints is called inherent model-based constraint. So when we talk about the inherent model-based constraint, we talk about the constraints that are already inherent in the relational model. For example, in the relational model, inherently, it says that you cannot have duplication tuples. So if these constraint is already within the idea or within the what the model has to do, then we call it inherent. The next set of constraints is called the schema-based constraint. This would happen when you design the schema for that particular database. So when you do it, we'll use the SQL to write out the constraints here. And basically, we'll use the SQL called DDL, or Data Definition Language, to specify the schema-based constraints. For example, we can say that phone number must consist of 9 numerals, for example. So these would be written out within the database, all right? Because usually if you only have phone number, okay, let me ask you this. If you want to design a database to keep the phone number within the systems, would you be using just like integer? Would that work? It wouldn't work, right? Because integer would not even allow 0, a leading 0. So it can't work that way. Now, you probably said, yeah, I'm going to use string. But if you would open to like 50 strings, then you can enter anything in there, right? So if you want to maintain, or you want to make sure that you have the least errors it could be, then you could design these schema-based constraints such that the data that will be kept within the database would have to be verified before it is entered or it is saved into the database. Now, within the database, it cannot really you cannot really keep every constraints there are. In that case, other constraints that cannot be handled by the database will be handled at the application level. So when we have to take care of the constraints within the application, we call it application-based constraints. For example, the value must be in Thai language. So these cannot be expressed within the schema. So you have to write it out within the application itself, right? Now, since there are three different things, inherent model-based constraints, these are the nature of the relational model itself. So you can't really have anything to do with this. I mean, meaning that when you write the database, you do not have to write anything that is, you can't really do anything to contradict the database nature. Also, the application would have to be handled at the application level. So we are going to focus on the schema-based constraints, right? Now, for schema-based constraints, there are 5 different constraints here. Domain, key, entity integrity, referential integrity, and other type of constraints. So basically, we'll be going through each one of them. And the first one is called the domain constraints. Domain constraints is quite easy. It says that within each tuple, the value of each attribute A must be atomic. It means that the value is indivisible. For example, if we have address that comprises a street number, and street name, and zip code, so and so, then it's not atomic. So to be atomic, you have to separate each of the data, within what you want to keep and make it atomic or indivisible. We'll have more examples later on. And within the domain constraints, one is saying that it must be atomic and it must be in the same domain. All right. So just these two things, just 2 words here. Being in the domain constraint, it's a atomic and must obey to the domain that you set. All right. Now, the data within the database that you keep can be anything or can be any type. For example, integer, real numbers, character, booleans, data, timestamp, or subrange of value or enumerated type. Do you still remember what subrange and enumerated are? You remember? You want me to go over it again? Yes? Okay. When I'm talking about enumerated type, it's I give you example. For example, that if you are going to put into the database, the sex of a person, right? You can have different things that you choose from. If you allow the user to put anything in there, it could be string, right? But if you say you can only pick this set, for example, I said, female, male, or no response, or whatever you have. If you have the list that the user can pick only one or another, then it is called enumerated type. What a subrange means that you have a range of value that you allow. For example, you can say that you allow user to enter their age by themselves, but the age must be between 15 and 40, for example. So there's a range that is allowed within the database. All right. Okay. You can take a look at you could probably take a look at like the drop down menu. Something that drop down menu. It means that within the database, you can say that if I call it a province, for example, I have an attribute called province, and I define it as enumerated type. The type of province could be from like กรุงเทพ Bangkok, and all of the provinces in Thailand. Okay? Right. Okay. Now, first thing is domain constraint. This is easy. Just 3 words, atomic, within the domain, and could be any type of the data types here. Now, next one is called key constraints. All right. What I'm saying here is that a relation is defined as a set of tuples, right? So you have a relation, you have many, many, many tuples. All right. The idea of key says this. It says that all elements of a set are distinct. It means that each of the tuple must not duplicate. All right. So, or the other way I can say it here that no two tuples can have the same combination of values for all of their attributes. For all of their attributes. So if, okay, let me switch this a little bit. So you can see that the example here, no two tuples have the same, exactly same data in it. All right. Oops. So that is what I'm trying to say here. But I'm also saying here that usually there are other subset of attribute of R with the property that no tuples in any relation state R of R should have the same combination of values of these attributes. What I'm saying that the first line is that all element cannot be duplicate. However, if you set the criteria that these subset, not the whole, not every attribute, but only subsets of the attribute cannot be duplicate, then you will be offering something called key. All right. Now, there are two types of keys. Many types of key here. Actually, I have four names in here. The first thing is called a super key. All right. When I'm talking about a super key, it means a set of one or more attributes can be just one attribute or more attribute in the relational database that uniquely identifies a record in a table. So it means that, for example, here, if I don't think about anything at all, I say that, well, for the car relation, can I put state, registration number, serial number, make, model, and year as key? It is yes, right? Because none of the tuple here would duplicate. So the whole thing can be super key. But when we talk about a key, it is a subset of the super key, which is the minimal super key. When we talk about minimal super key, it means that a key that is super key and you cannot remove any other attribute such that it will maintain that the tuple will not duplicate or still unique. All right. I'll show you the example on the next slide. But if a relation has several candidate keys, I'm talking about more keys here. If it has several candidate keys, one will be chosen and it will be called primary key. All right. So now there are four terms here: super key, key, candidate keys, and primary key. Let's take a look at the example on the next slide. I have a car relation schema, right? The default super key would be like every attribute. You can make all the every attribute such that each of the tuple would be unique, right? But if you take a look at the data in here, if you can still remove some of the data and it's still unique, then it's not a key. It's still a super key. All right. So in here, if I remove year and I have the super key as state, registration number, serial number, make, and model, it's still a super key because you remove the year and it's still unique, right? So I'm going to give you here the schema here. I say there are two possible keys. So I say state, registration number. If you have state and registration number here, can be key, right? Or you can have serial number. So serial number is also a key. But can make be a key? Cannot, right? Because you can still see duplicate tuples if you make a make being a key. But can you actually use make and model? You know, if you only have these 6 lines, can make and model a key? Is it possible that does it make it unique? It does, right? Because there are no two tuples that make and model duplicate. Because if you use make and model together, you have Oldsmobile Cutlass and you have Oldsmobile Delta. There's no duplicates there, right? Because these combinations do not duplicate. It can be a key, but not a good key. All right. So anything that can identify or make the tuple unique can be a key and can be a combination of different attributes altogether. But you have to select the good key as well. So now I offer 2 good possible keys here. one is state and registration number, and another is serial number. So these are the good keys because you cannot have any duplicate anymore, such that when I'm talking about the super key, let me give you another example. What if you use serial number here, and make? Is it key or super key? Serial number and make. Who say it's a key? Who say it's a super key? Yep, it is super key, right? But you can still remove make, and serial number is still unique, right? However, let me do the opposite. What if I say serial number and make and set it as a super key? But if I remove serial, I only have make left, right? But make does not have a characteristic that makes every line unique. So make cannot be the key. All right. So again, the default super key of any table is every attribute put together. That is the default. Now, to define what a good key is, if you don't know the meaning of anything, then you remove each of the attribute and say, well, if I remove this, is it still unique? If I remove more, is it still unique? Until you get what you cannot remove anymore, and that would be the key, which is a minimal super key, all right? But now this one is easy because you know the meaning of registration number, you know the meaning of state, you know the meaning of serial number. But many times when you do not know the meaning of each of the attributes within the database, the only thing that you can obtain the key is to try to remove each of the attribute to see if all the tuples are still unique. All right. But usually, in real life, you are the one, database designer would be the one who set the key for the table. So you naturally would know the meaning of the database, the meaning of the key already, right? Now, so we have finished two of the constraints here. We have done domain constraint. We have done key constraints. Next one is the entity integrity constraint. All right. The entity integrity constraint says that within the relational database schema, a set S, okay, which is a schema, okay, of a relation schema belong to the same database as here, S is the name of the database. And in entity integrity says that the primary key, okay, primary key we talked about last time, right? We call it PK, all right? Primary key of each of the relation in the schema cannot have null values in any tuple. It makes sense, right? Because if you want one of the attribute or set of attribute to become key, you cannot leave null value, or it wouldn't allow it. So when we say entity integrity number one is that for any key cannot have null. So you can write it down. You can write it mathematically as tuple. Okay, within each of the tuple, you can take a look at the primary key, and the primary key of any tuple cannot be null, right? Now, however, I put a note here. It said other attribute of R may be similarly constrained to disallow null values, meaning that, of course, for primary key cannot be null, but you can choose other attributes, although they're not primary key, and set it as null. That is doable as well. Now we already finished our three constraints there. Let's take a look at how we are going to use it. For example, I have a schema diagram of a company relation database here. I have an employee, the schema, the first relation is called employee. And within the employee, we have attributes, right? We have if name, a minute, so and so. And the second relation is called the department. Third relation is called the locations. Project works on independent. So if you are familiar with the last ER diagram, if you remember, what we are going to do in this session is to translate from ER into this relational database schema. Okay. So this is called relational database schema. It looks like this. Now, this is one possible database state of the state of, I'm putting something, of the company database schema here. So let me show you. Oops. Okay. This is actually the schema, right? Because we are talking about just the structure of what it looks like. We don't have the data in here as yet. Now we have the data. So we have instance of the database at one point, all right, at any point in time. So we say that at this particular snapshot, we have the employee relation with these particular data, so and so. So these are the instance within the database, all right? So we can also call the state, a possible database state. Now, if you are using the database, you probably enter a new employee into the database, then the snapshot or the instance or state will be different. So the state of the table or state of the relation would be changing all the time if that database is in operation. But some of the table or some of the relation may not be as how do you say, may not be as dynamic as the other. For example, let me give you some of the examples here. If you have new employees all the time, then that particular table at that particular relation might be moving a lot, right? Or might be having like new data or deleted data. But for the department of the company, the data within the department may not change a lot over time. So it really depends on how you are going to assign the storage for each of the table as well, right? Now, so for reference, so this is what we call the entity integrity. So let's finish the entity integrity once again. So within the entity integrity, it's quite easy. It says that you have to assign a primary key, and you have to make sure that primary key cannot have null values. All right. So that's the entity integrity. The next one is called referential integrity constraint. So for the referential integrity constraint, it would involve two relations. So we say that in two relation, we call it, one is the referencing relation and the other one is referenced relation. So it means that relation will be related, right? You remember the ER diagram, you have entity and relationship. And relationship would be dealing or would be connecting between two or more entities. But now we'll be calling these the referencing relation and referenced relation, which actually define the same thing. All right. So what we do in the referential integrity constraint, saying that the tuples in the referencing relation, let's call it R1, would have the attributes of FK. This is a new set of key called foreign key, right? In the previous slides, we have super key, candidate key, and primary key. Now we have another set of key, another type of key called foreign key, right? We will choose any attribute that would be linking between the relation and set it as foreign key. So we only have foreign key when the two or more tables are related, right? Now, the way we write it out mathematically, we can say is that T1 here, and we put bracket, and for foreign key, we say FK. It would be equals to primary key in the other tuple. All right. Okay. So we say that tuple T1 in R1 is set to reference to tuple T2 in R2. So these are two different relations. You want to relate two relations together. The only way that you can do it is to set something called foreign key. So foreign key is one of the relation must be equal to the primary key in another relation. All right. You relate the two relations. One, you must have primary key. The other one referencing it would be called foreign key, right? You'll see more of the example on the next slide, all right? Okay, so in the referential integrity constraint, we will display it using the line to connect between the two relations. You can see it here. Okay. So within the schema that we see here, you have employee, department, location, project, works on, and dependent. let's see how foreign key looks like. So foreign key are those lines that connect from one to another. For example, if we are talking, I'll show you one of the easy ones. Let's take a look at the employee and the dependent. So for dependent to be linked or to be referenced to employee, you will write the line from the, to link the primary key and foreign key here. So ESSN here is the foreign key reference to the primary key in employee table. All right. Okay. Vice versa, you have project here and you want to relate project with the department. You have DNUM here, which is the foreign key connected to D number in the department, which is the primary key. So DNUM again is a foreign key linked to primary key of the department. I'll show you later. Okay, I'm showing you at this step. It's an easy one first, but this is how they are linked together at the end. But I'll show you each step of how each of the lines happen and how if you remember from the ER diagram, we have employee, we have department, we have project, we have dependent, but we don't have depth location, we don't have works on, but how these are translated from ER diagram into relation schema. Okay, it'll be step by step in this class. Other type of constraints that I want you to know is are called semantic integrity constraints and functional dependency constraints. We'll actually go through functional dependency constraints when we do normalization. So that would be like the 2 classes after these. But for semantic integrity constraints, actually it's based on application semantics. So it cannot actually be expressed within the database model. It will have to be taken care of at the application level. For example, I could say maximum number of hours per employee for all projects he or she works is 56 hours per week. This mechanism would have to be done by the applications, and you can set something called triggers. So we'll also do triggers. We'll write triggers within the database in our class as well. For functional dependency, is another type of constraint. We say that we will establish a functional relationship among the 2 sets of attributes. Let's say attribute set X, attribute set Y. So we say that the value of X would determine the value of Y. For example, I say that if I know that the citizen ID is this, I would know exactly the name of that person, right? So it's the dependency from one attribute to another. Okay. Now, another thing that we have to know about the constraint is that when we do the update operations on relations, all right, for the update operations, we probably insert, so that's the one type of an update, or we delete the data is another type of update, or we modify the data is one type of update as well. So you can insert a new tuple, you can delete a tuple, you can change value of the existing tuple. All of these actions or all of these operations may violate the database, right? But you have to make sure that when you input or when you operate on any of these, you should not violate the integrity constraint, right? Integrity constraint. Do you remember integrity constraint? จำได้ปะ? What does integrity constraint says? Oop, let me go back. I believe it's here. So, entity integrity constraint says that for the primary key, you cannot have null values, right? So let's take a look again. If you insert a new tuple into the database, you will violate the integrity constraint if when you insert and primary key is null, right? So it would not allow that to happen. Or when you delete data and you said that well, I'm going to delete the primary key. That is not possible. So because it would violate the integrity constraint. Or if you modify the data such that, you delete primary key values, or you modify the primary key value to be null, then you also would violate the integrity constraint. So make sure that when you insert or delete or modify the data, it does not make the primary key null. All right? Okay. So, I have like more information here. So let's say the insert operation, you provide list of attribute values for a new tuple, and it probably will violate if you do this. Domain constraint may be violated, if you insert a new operation in there. Sorry, if you insert a new data in there, what would you do to insert and then violate the domain constraint? If you remember, domain constraint says what? Domain constraint say it has to be atomic and it has to be within the domain, right? Within the same domain. So if you insert the data and it does not correspond to the domain you set, then you say that it violates the domain constraints. Now, for the key constraint, it says that the key cannot be duplicated. So it means that if you insert the new data and it duplicates a key, then you violate key constraints. And if you enter the new data and the primary key is null, then you violate the entity integrity. And for referential integrity, if the foreign key in one of the table is null, then you cannot link to the primary key of the other table, then you violate the referential integrity, right? Same way, you can also think of the previous slides when you do the delete operation. So, but delete operation is something that I say you really have to take care, or you have to be very aware when you delete any line of data or any tuple, because actually, if the tuple delete can be violated only referential integrity. All right, it does not violate. Let me see. It does not violate domain constraint because you delete the data, right? Let's say that you are deleting one tuple, then it cannot violate domain constraint because there's nothing to do, right? Key constraint, you delete it, doesn't have anything to do. Now, what would matter is only when you delete, what only matters is the referential integrity. What does it mean? It means that the tuple being deleted is referenced by the foreign keys from other tuples in the database. If you take a look, let's say that I have employee table, right? And I have dependents table. You follow me? I have employee and dependents. What if I delete an employee who have dependents? If I delete the employee who have dependents, then the information about that dependent would not be valid because it doesn't have anyone to relate to, right? So if you delete any tuple, you really have to take a look at the referential integrity, whether the data that you delete have anything to do with foreign key in other table. So the way that it could be treated, there are different ways here. If that happens, one is to reject the deletion. So you said, oh my God, I probably have something referenced there. So I would not be able to, you would not let the user delete that particular tuple. Second is attempt to cascade or propagate. It means that the deletion by deleting tuple that reference a tuple that is being deleted. What cascade means here is that if you delete that employee with possible dependents, you must also delete anything related to it. So you delete one person with dependents, you must delete dependent that belongs to that particular employee as well. So that means cascading operation. You got it? Okay. All right. Okay. That's called cascade. Another way to handle this is to modify the referencing attribute values. So whatever caused the violation, you can set it to be null or change it to another valid tuple. It means that if you have you still have the dependent, and you want to keep that dependent information, you have to change the value within the foreign key. All right. For example, I have dependent, right? That belongs to this particular employee. Now, I probably would change the dependent information or the data such that this particular dependent may belong to another employee. All right. Okay. But if the meaning of that particular data is not true anymore, we would not use it this way. Most of the time, cascade will be used if the data connected to it cannot change the meaning. However, the example that I gave you before, let's say that that dependent may have parents, they probably have mother and father within the same company, then we can change that particular parents to another, like from father to mother, mother to father, for example. All right. And the next, another way to handle it is to execute a user-specified error correction routine. It means that you just write out what you want to do. For example, you can write an application further along that particular operation, saying that, oh, you have to change this, or you have to take care of this, or you would allow this particular data to be changed this way. So if you have any details to keep that particular data that needs to be changed, then you can do anything about it. So execute a user-specified error correction here. Now, I have a note here, a very important note, that if the referencing attribute is a part of PK or part of primary key, it can't be set to a null value. So basically, when I was giving you the example of dependent, that you can change some of the values of dependent, but if it's a part of a PK or primary key, then it cannot be null, right? You have to change it to something that is not null. But again, let's go back. Usually, in real life, you use the first two, which is the rejection of the deletion there, or attempt to cascade. All right. Now, for the update operation, it can violate any of these because you probably change the domain, you primary key might be null, entity integrity there, and then you remember entity integrity, right? The primary key has you have to have the key, and you have the primary key cannot be null, and then referential constraint saying that foreign key linked to the primary key cannot be null as well. All right. Now, okay. Now the part when you were asking like why I have so many lines there, and why there are extra schema happen in the schema diagrams, that is extra from the entity relationship diagram. All right. So there are mapping steps here. Let me go through a few easy ones before we take a break, right? What we'll do, which is actually one of your homeworks as well. The homework number one would be dealing with, I'm giving you the scenarios, and then you write out here on the left side, which is the ER diagram, right? And then on the assignment number two is to translate from ER diagram into the relational schema on the right, right? And this is the example of the final relational schema that you will see from the left one to the right one. Left is ER, or entity relationship diagram, and right is called the relational schema. Okay. Step number one is to map from the regular entity types. All right. Is to map regular entity types only. So the first step is to look for regular ones. How many are there? How many regular entity types are there? Okay, let's see. Uh, 3 or 4. Who say 3? Who say 4? Okay, let me see. First one is employee for sure, right? Okay. Second one is department. Third one is project. What is the 4? No. Because I'm looking up for regular entity types, but dependent is a weak entity type. All right. So regular entity type are those with single lines. So we only have 3 here. Okay. All right. So I actually already put the answer down here. So you will not be confused. So you can see the result down here that I'm mapping just the employee, department, and project. So for the first step, you take a look at the strong or regular entity type. All right. You list out the name and then you list out the attributes of that particular entity. All right. Also, another thing that you must do. Okay. The next step that you must do, I say, choose one of the key attributes of that particular entity as a primary key for the relation, for that relation R. And if the chosen key of E is composite, then you set simple attributes that form it, that form it together, form the primary key of R. What I'm saying here is that it does not have to be just one particular attribute. It can be a composite keys as well. Okay. However, I'm saying that for each regular strong entity type E in ER schema, create a relation R that includes all simple attributes of E. Now, the key word here is the simple attributes. Okay, let's take a look. For employee, I have employee here. Let me annotate. Okay, I have employee here. And I translate it to relation called employee. All right. For employee, I said includes all simple attributes. So simple attributes are what? B date, SSN, sex, address, salary. These are simple attributes. But now I also have the name, but name is a composite, right? Name is a composite attribute. I wouldn't take the name here. I'll just do simple. So I only take first name, middle initial, and last name. Yeah, you only take the children. You don't take the parent. So see, you have 1, 2, 3, 4, 5, 6, 7, 8 here. I don't have this particular one because it is not a simple attribute. It's a composite attribute. I want to take the end product, which is the children part of it, if there are any nested attributes there. All right. Now, for project, let's take a look at the project first. Oh, by the way, and I with employee, I see that SSN as a key, right? So I underline SSN here. SSN is underlined here. Now, let's take a look at project. I say, yep, of course, I'm gonna do project relation here. I write out project relation. I take simple attributes, name, number, name, and location. However, I say that here, only choose one of the key attribute as primary key for R. But here there are 2 different possible projects because name may be unique. Project number is also unique. So I just pick one. So that's why I pick P number here as the key and underline here. And I don't underline name because I only pick one. The question is that, can you just underline P name, make it primary key and not making P number a key? Is it possible? It is, right? Because you know that name is also a possible key, but I'm not using it. You can just pick one. All right. Exactly. Now, for department, I left it last because let's take a look at department. I have name, number, and locations. Take a look at this. I do name, I do number here, but I don't put locations here. Why? Exactly. It's very good. Because you have the double line on location, it means that it's multi-valued, right? So multi-valued is not a simple attribute. It's multi-valued attribute. So I don't do anything about that at this moment. Get it? All right. So the first step at all, take a look at the entity type that is a regular type or strong type, all right? Which shown by single line around single rectangle there. And then you take all the attributes, but remember, they must be simple attribute. So multi-valued attribute will not be included in this step. And also for composite attribute, you only take the simple attribute after the composite attribute and put it in here. So this is the very first step, is mapping just the regular entity types. All right. Now comes to step 2. For step 2, you take a look at the weak entity types. So weak entity types here, we have dependent here, right? So what we do, I say that for each weak entity type W, all right, in the ER schema with owner entity type E, so we can say that, oh, okay, I have dependent as schema and its owner. Owner is, you can specify the owner by this line here, right? The relationship say, well, owner is the employee for sure with this link, all right? So what we do is we say, create a new relation called relation R. So I create dependent relation here and include all simple attributes, okay? All simple attributes. So say, okay, here are my simple attributes within that dependence. I include them here, okay? Now, in addition, I said, include as foreign key attribute of R, the primary key attribute of the relation that correspond to the owner of entity types, owner entity types. So the owner entity types is employee, right? So in employee, you have SSN as key. So what we do here is that, try to follow me first, okay? Let me do it again. I said dependent, I said out dependent here. For dependent, I have name, I have sex, I have birth date, and I have relationship here. What happened with this ESSN? ESSN came from this step saying that if it is a weak entity type, you must take the primary key of the owner entity, which is SSN, right? And include it as foreign key. So I put these in here. And now what I need to do next is set it as foreign key. So I must draw a line to signify this. Get it? So this show foreign key relationship, I create an ESSN, which is the primary key from that employee or the owner entity type. And you have to draw the line here, but I didn't show the line on the slide that I gave you. Okay. So right here, I also say that the primary key of R, okay, is the combination of the primary key of itself and also the owner and the partial key of the weak entity type W, if any. All right. So the primary key of the owner is the SSN. So I have to assign it as primary key here. And also from dependent, you see that you have partial key underline, the dotted line under name, right? So you have to make these two a key for this dependent table. All right. Okay. Say again. No, it's not super key. It's a key because if a super key, let me say it, correct. This is a key, a minimal key that is also a composite key. What I mean is that if you have these two, it's not a super. Let me say it again. Anything could be super key, but to be a key, it has to be minimal. So if you have ESSN and dependent name, it is a key because you cannot remove anything which makes a table still unique. So a key is a minimal super key, but if you have key which is a composite of many attributes to make it a key or even a minimal key, it means that that set cannot be you cannot have less attribute and still make it unique. Yes. Well, for super key, it's unique anyway, but you can still remove some of the attributes out of the set of key because it's not necessary to make them key. Okay. All right. So at the end of this step, actually, this is not finished. The other thing that you should have is the line from this ESSN here pointing to this SSN because the foreign key has to be shown in this step as well. Okay. Now, let me go to the next one and then after, oh, actually, let me finish it here for now and let's take 10 minutes break. And then after that, it will be like, yeah, the rest is quite long. But yeah, let's do 10 minutes break now. Okay, let's continue. Whoops, sorry. I actually turned off some of the ACs because it's really cold. So if and I'm not sure which part that AC is operating. So if it gets like too warm, let me know so I can turn AC back on. But actually I just turned down, I think I just finished two of them. So the other three are still operating. Anyway, uh let's continue. Okay, now we come to step 3. If you remember, let me recap real quick. So for oops, step 1, we only take a look at the strong or regular entity type. So we have employee, department, and project there. And then we take only, and only simple entities. So anything that is not simple, we're not taking them. So for composite attribute like name, we only take these atomic, which is F name, M in it, and last name. But for these locations, which are the multi-valued, we are not doing anything about locations at the moment. And then when you choose the key, you only choose one. If there are uh, several possible keys, you only take one. All right. So you choose the primary key here. The second step, we do the weak entity type. So the weak entity type identified by double rectangle here. What we do is that we take all we create a new relation and include all the entities from that relation. And then we take the key from its owner to include as part of the key or the composite key. So the composite key composed of the partial key from that relation plus the primary key from the owner relation. All right. Now comes to the third step. Third step. Now we have done all the entities types. So now we are taking care of the relationship types. Let's take a look at the relationship type 1-to-1 first. All right. 1-to-1. We have 1-to-1, one-to-many, and many-to-many. So this step number 3 is 1-to-1. For this particular example, which one is 1-to-1? You have managers only, right? Only one. Now, what we do here, there are three ways. What we are doing at the moment is way number 1. All right. I have number 2 and number 3 on the next slide, but let's take a look at how we handle it with this first attempt. All right. I say that if for the binary 1-to-1 relationship type, identify the relations S and T that correspond to the entity types participating in R. And there are 3 possible approaches. Number 1, say, choose one of the relationship and call it S and include the foreign key in S, the primary key of T. What I mean is that we have to take a look at the 2 relations that surround that relationship and then take the key from one of the entity and put it in another. All right? Okay. ทำไมนะ มีอะไรเปล่านะ Okay. But I am also saying that within the managers, we have to choose, let me do this. Let me get this drawing tools. Okay. Now, so let me take a look. Follow me. Oh, which one do I use? Pen. Okay. We have managers here, right? We said that managers, you have employee and you have department connected between this relationship. Now, we are going to take a look at the primary key on both sides. What we are going to do is to take one primary key and put it in the other. But which side, right? What it recommends is that take a look at the total side. So total is here, right? The double line here is a total side. For this, you will see that I'm taking a look at the total side, which is the department. And I am including the key from the other side, which is the SSN from employee, and add it in here. Can you see that? So this is way number one. First way is to take a look at the one-to-one relationship and see if there is a total and partial. If there are total and partial, then you take a look at the total side and then put the key from the other side or the partial side into this total side. All right. So that happens, right? Manager SSN from here. I rename it to make it not duplicate. So I have denamed the number and I add manager SSN here.
We have partial participation on one end and full participation on the other end. Then the entity from the partial participation will be the foreign key, the key from that. So that will be the foreign key from the entity that has a total participation. Is that correct?
No. It doesn't have to do anything with foreign key at the moment. No foreign key. So oh, okay. Yeah, you're right. You're right. I'm sorry. Yes. So first step is to identify which is which, right? I mean, take the primary key from the partial side and put it in the strong side. And then you link, yes, exactly. You link the foreign key. So after this, what you do is that you write manager SSN and point it to SSN there. Exactly. Thank you. That is the next step here. So the next, number two, okay, you can do this. It's called merge relation option. So this is an alternative mapping of one-to-one relationship type, right? By merging the two. So this may be appropriate when both participation are total. So when merging, it says that if you are merging them, then you put employee and department together to form just like one big ones. So you don't have department here anymore. So employee will have blah, 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 and then you have department connected to it. So it will form like one big relation here. So that is called the merge relation option. Now, the next one is called cross-referencing option. So this alternative is set to you will set a new one. You will set a new relation and cross-referencing it. So what happened is that, oops, sorry. So for this third option, what you do is that instead of having the manager SSN here, we don't do that way. What happened with the third option is that we are going to, okay, we are going to form a new one. So a new relation, maybe I'll call it managing or something like that. And then I will take the key from one side and key from the other to form this one. You get it? Okay, let me repeat it again. First approach is good when you have one side total, one side partial. So what you do is only to fix on the total side and take the key from the partial side, put it in the the total side, and then set the foreign key. The second option is good when both are total participation. So when both are total participation, you merge the two relations together. But now, once you merge the two relations together, you have to have the key for the new relation, right? For this big relation, the key would become the key from both sides. So you now have a composite key as your key, right? The third way is to create an extra relation, new one here, and only take the key from the side. So let me ask you, if this line is let's say that this line is only partial, so it's partial and partial, and I want to do the third one here, what is it going to be? What kind of attributes would be in this third relation? Is its new relation? Okay, the question is that for these three different options, right? The third option say that you create a new relation, and within the new relation, you only keep the attribute which are keys from both of the entity related to it. Right. So when you have this one, you can only have SSN and number here. And number here. All right. And the rest, you don't have anything because you will link. Let me change the color. Then for foreign key, you will link this back to SSN and link this back to the number here. You get it? All right. Okay. You can do all three, but it's only that the first option is good when one side is partial, one side is total. The second option is good when both are total. And the third one, you can choose to do it any way you want. All right. And usually what I like is actually the third option. I usually do the third option, but it's not necessary. You can do the second option. But if you choose to do the third option, this will not happen, right? Because this only happen when you do the first option. So when you do the third option, you will have these extra ones. Here. So if we do the third option, you will have this next one, right? Can I write it? Okay, so this option will call, let me call manage. This is really hard to write. So this is manage, the new one. So for the manage here, I have SSN from employee, right? I call MSSN, and I have department there. I just want to name it department number. All right. And then next step, what I do is I'm gonna do foreign key to link this to SSN and link this to the number, but I have to discard this because this came from option 1, right? So if I do option 3, the final would be employee, department, project dependent, and then this manage, the new one with these two. But I have to underline these because they would compose composite key for this third option. Okay? It's not entity, it's a relation. Entity come from ER diagram. So for this, it's no more entity, it's just relation. So this is another relation called manage. And within this manage, you only have MSSN, MDNO, and then link the foreign key back. And that's it. Okay? All right. Now, so we are done with step 3. Now we come to step 4. For step 4, we are taking a look at the 1 to n relationship types. So 1 to n, oops. Oh, I forgot to do this. Okay, discard this. It's not. Okay. Now, for m to n, let's take a look which one is n to n. It works for here, right? 1 to n. You have works. Oops, sorry. Wrong one. Let me clear. Okay, let me do it again. Discard this first. This is an extra one. Okay, now. Okay, let's take a look at 1 to n. So 1 to n relationship I have works for, I have controls, and I have supervision, right? Okay, let's take a look. Oh, those weak entity. We already took care of the weak entity. Yeah. So now, if we take a look at 1 to many here, we have 3, right? So what we do here, it says that for each binary, regular binary 1 to n relationships type R, identify the relation S that represent the participating entity type at the n side. Okay, at the n side. So we have 1 to many. So we take a look at the n side first, and then include as foreign key in S the primary key of the relation T that represent the other entity type participation in R. So the wordings may seem a little confusing, but let me show you how to do it. We also include any simple attribute of that relation as attribute S. So what happened is that, let's take a look at the first one, project. We have controls here, right? So for control, we have 1 to n, which side is n? The n is a project side, right? Okay, so we work on project side and then take the key from department, because you have n here, 1 here. You have key, which is number there, and then put it here. So I said dnum. I just want to rename it to other things. So dnum. And then what you do is you have to do the foreign key from dnum. Oh no, that's it, right? Because you already related. Now, the second thing that you need to do, dnum, project dnum. Oh, you still do that. dnum. You connect it to department here. Here is the link, right? And then the next step is do the works for. So for the works for, you see that the n is on the employee side, right? And then you include the number from department here. You see that? And then this D number we have to be linked to department, right? See that? Okay. And then finally, we do the supervision. Because supervision is a recursive, right? So then that's why I have the super SSN here, which links to itself. See that? ค่ะ ยังไงนะคะ Yes. Still. Yes. It's recursive. Okay, so this mapping of 1 to n relationship types. Again, let me recap this. When you have 1 to many relationship, you take a look at the many side to be the main relation, as a main relation. And then you include the key from the other side, which is the one side, and then take that key as the extra on another attribute, and then you set the foreign key to link between the two.
Participation, partial participation. So for example, here we figured out that the number can be the foreign key for employee from department number. But how do we know whether we have to use the department number as foreign key or whether it has to be the other way around? And take the employee then as foreign key, like because over here it's like 1 to n, but it's total participation. What about the other one, which is like 1 to n, but 1 is partial participation and n is full participation?
Okay. In this step, if you do the one-to-many relationship types, you don't have to take a look at the part, whether it is partial or whether it is total. So when you do the one-to-n relationship type, only take a look at 1 and n, and use n as the main one, and then link the one to it. So you don't have to do anything with the partial and total. So partial and total, we only do it at the if it is 1-to-1. So if it's 1-to-1, you take a look at it, like which one is stronger. You said the total is stronger, right? You take a look at that. But now if you do one-to-many, many is the one that you need to be linked to the main one. So you take a look at the n side. So with 1-to-n relationship, only take a look at the n. Okay. Now, from many to many, it will be different because from many to many, let's say that we have in here, you only have works on, right? Now, because you have, oh, what actually, I haven't finished the other one. Did I finish the other one? Managers one. Okay, here for works on, you can see that if it's many to many, what we do is that it says create a new relation, right? Create a new relation. That's why I have it here. Create a new relation. And then within this relation, what we do, we said include as foreign key attribute in as the primary key of the relation that represent the participating entity types and their combination. So for works on here, you have employee and you have project. That's why I have, I need to do another thing. Employee and project. You have, I say WSSN here and also P no here, project number here. I forgot this. I have to underline underneath this because I have to form the composite primary key. All right. And then because I have hours, I have to also list the hours here, but this is not a key or anything. So I need to have the extra one here. And then I would have to do SSN works on back to the employee. And also P number backs to project. And that's it. Okay. So this is many to many. Yes.
One create as a separate relationship and we try to link the keys and that would be the foreign keys to the other.
Exactly. Yes. Okay. Now, step number 6 is on the mapping of multi-valued attribute. If you remember, we have not done this part. Remember? When we did the first step, we have the strong relationship type of strong entity type, which is department, and we only take simple attribute, which is name and number, and we leave out locations, which is multi-valued attribute. Now, we are going to take care of the multi-valued attribute this way. Okay, so what we do here is that for each of the multi-value attribute, it says create a new relation. So that's why I have this new relation called department location. And then I would include an attribute corresponding to A plus the primary key attribute K. So I would take its attribute, which is the location, but the primary key of this is the number, right? So I call it's department location. So I call it DL, department location number, and D locations, which comes from here. And then it also says that it's a multi-value, right? So we need to assign the number and the location. Yeah, I have to have 2 lines here. DL number and DL location. I need to underline this. I forgot the underline here. All right. And then you have to link the number to department number. Okay. But the location, you don't have to do anything because it's a new one, right? But remember that you have to put it as a composite key here. I forgot the line there. Okay, let me show you this. If you don't underline the DL location, D location, what happened is that you only have DL number, let's say DL number 1 and location Bangkok. But then you cannot have DL number 2 location, DL number 1 with different, department number with the same location. It's okay when you do one, right? But if you have same department number in many locations, you have to assign both as key because now you can have department number 1 in Bangkok, department number 1 in Chiang Mai, department number 1 in London. So both of them have to be composite key, otherwise it would not be unique. Okay? All right. And then, so this is after 6 steps, now you have all these.
The multiple value of the application.
Okay, sure. So for the multi-value, which is step number 6, we only have multi-valued here, right? In locations. So when you have multi-valued, you always create an extra relation. So when I create extra one, I create this depth locations here. So once I created it, I have to understand what would be included as entities within that relation. So first entity would be that particular one, right? I mean, that location's there. And I also have to take the key from that department. So that's why it has this, this number is this one here. And location is here. But it's not done there. It is done when you assign both of them as keys. So both attributes will form composite key. And then you link the foreign key DL number to department. Because it's the only attributes that appear within the whole thing. So you don't link it to anywhere, right? It's not a foreign key. Okay. Good question. All right. So this is the whole thing from what we have done, you know, the 6 steps. But now we have the EER, if you remember. Oh, sorry, not the EER yet. Not yet. Okay. Now, step 7 have something aside from this. We don't have so from here we are done with the mapping there. But for step number 7 here, if there are any relationship types that link more than 2. So far we have done just the binary relationship types, but here I'll show you the ternary relationship types. What it means is that for this supply, there are, 3 sides, right, out of it. So when you have this, the relationship types that has more than 2 connections there, okay, what you do is that you will always create extra relation, right? So for each n-ary relationship type R, where n is greater than 2, create a new relationship type S to represent R. So what we do is that include as foreign key attributes in S the primary keys of the relations that represent the participating entity types, and include any symbol attribute as well. So what we do here, you can see that supply here would become, you see this from supplier, and you let me change the color. Okay, that's okay. And project here would be you have new relation, and for parts here you have another relation. So you create one relation for each of the entity that connects to the supply relationship.
Let me say the supply
It doesn't have to do anything with a super key at all. So basically, let me say that again. Let me try the other way around. So when you have ternary relationship, first of all, if you see the results here, what you do is that you take each of the entity and convert it to relation, right? One entity to one relation, one entity to one relation, one entity to one relation. So what are included is you take whatever all the entities that you have in there. So this entity comes here, its entity comes here, and its entity comes here. Okay? If there are more entities, then you list all the entity from that particular sorry, not entity. You list all the attributes that they belong to. And then next step, you create another relation, which is a supply here, but you only take the key from each one. You only take the key from each one. And then if there is any attribute belonging to that particular relationship type, you also take that there. So these three attributes will be formed together to create a composite key, but not super key. So now it is composite key.
case, then we see that it's not
No, this is minimal because you take key from supplier, you take key from project, you take key from part. So if you don't, it will be super key if you also assign quantity here as key. But actually quantity is not needed as key. But if you remove anything from this, you cannot, right? You cannot remove part as key as part of the key. So it's not a super key. It's a key because it's already minimal.
relationship itself has its own unique attribute, which when assigned to it, combined with the other relationship, then we
You probably have a super key, but actually it's not needed, right? So you have to, in order to make it a key which is minimal, then you remove that particular attribute that is not needed as key. Then it becomes minimal super key, which is a key. Here is another example. If you have supplies relationship that connects to supplier and project, and then you have like, how do I say? You have three binary relationship. This is different from this, right? This one you have supply and you have ternary relationship, but here you have binary, but you have three binary, right? You have this is one binary, this is one binary, and this is another set of binary. So if you have this like looping thing, what you can do is that you will have suppliers here, you have project here, you have part here. So these would come from different entity and you make it relation, right? Three relations. But then what you do next is not instead of having just one big new relation here, you have three. So you have this supplies, can supply, and use here. So there are a lot of lines here. And what happened is that from the entity and you make it a relation, you only include the key, right? But for these relationship, you have to take the keys associated to it. For example, let me clear this first. Okay. Let's take a look at supplies, which comes from this one. For these supplies, you will take as key whatever comes to it. So supplies link between supplier and project, you have the S name and project name as key because it come from here, this one and this one. Okay? You don't have anything to do with part, right? But for can supply, you do the same. Can supply, you only take the key from S, you take S name and you have part number. And for users, you only do part number and project name. So it's like cyclic there. All right. So this is a difference between you have 3 binary relationship types or 2 or just one ternary one. Right. Now, step number 8 is mapping specialization or generalization. You remember the EER, right? Extended entity relationship diagram. So basically, when you map the specialization or generalization, you will have to convert each specialization with you have superclass and you have subclasses, right? Or you can say that you reverse it and you make the subclass to become superclass, right? Now, there are 4 different options. Option number 1 is called multiple relation superclass and subclass. Let's say that if you have this figure 1 on top, you have employee, which can determine by job type to be secretary or technician or an engineer. If you remember, the D would signify that it's disjoint, meaning that disjoint meaning that an employee can only be secretary or technician or engineer, but cannot be the combination, right? So for this multiple relation superclass and subclass, what we do is that we create a relation, L, let's say employee, okay, with attributes for C, and then for what would be the attribute? The attribute would be attribute from that particular ones, and then we also create uh relation that belongs to each of the subclasses here. So what you can see here is that you have employee, superclass, which is translated into the relation here called employee. So for an employee, you have social security number. You have just atomic one, right? F name, middle initial, and last name. You have birth date, you have address, and you have job type. But now you also create a relation that belongs to each of the subclass. You have secretary, technician, and engineer, which you have typing speed there. You have T grade there. You have engineering type there. But you also have to take the primary key from its superclass, which is SSN, and put it here. So you know which engineer has this ink type, which technician has this T grade, and which secretary has its typing speed. All right. So this is option 8A, called multiple relation superclass and subclass. What it means is that you maintain your superclass, you maintain your subclass. But by doing so, your subclass will have to include the superclass key into its subclasses. And that's it. All right, this is option called 8A. Now, option called 8B, it is called multiple relation subclass relations only. So what it means is that you use this when you want to maintain just the subclass, and then you take all the attribute in the superclass into this new relation. So for this type, you say create a relation Li for each of the subclass. So see, each of the subclass is car and truck. So you create one relation for car, one relation for truck. But now what you do is that you take all of its parents or the superclass attributes into it, plus the attribute of its own. That's why the car one has these 2 and these 3. So now you have 5 attributes altogether. And it is also true with truck. Now you have 5 because you have these 2 attributes of its own, and you add the 3 attributes from its parent or its superclass. So that's the final results when you do the multiple relations and use subclass relations only. So when we say subclass relations only, it means maintain just the subclass and take all the attributes that belong to superclass, add them to each one of the subclass. So now your relations only have these 2 lines, which is different from the first one because the first attempt you have 4 relations altogether, right? So let me ask you, if you choose to do these the one above, using 8A, what would be the number of relations that came out of 8A from this particular example? How many? You have 3, right? Because if you want to maintain everything, you have superclass and subclass, but you only take the key from the superclass to add into the subclass, right? Okay. Now option C. Option C says single relation with one type attribute. Okay. This is going to be, oops. Sorry. I didn't get this right. Okay. This is wrong. I have to change it. Sorry. So the result from this single relation is not this. Let us do it together. So single relation with one type attribute means that we need to create a single relation, just one relation with attributes. Okay, attribute would come from attribute every attribute union together. So it'll be attribute from superclass, attribute from subclass, all come together. Okay, and then we have something we said there is an attribute T, which is called a type or discriminating attribute that indicates a subclass to which each tuple belongs. So I have to change this. Sorry. Oops. Wait. I forgot to change this. So let's take a look at this picture here. We have the employee and we have job type, which is called the in here. A type of discriminating. When we say discriminating attribute, we say that job type is actually the attribute that can say, which employee belongs to secretary, technician, and engineer. We take a look at the job type. So if we do 8C, okay, we do 8C. Let me remove this, but I can't because I'm not signing in. So what we do is that, let me go back to this. We'll create a big one. So let me write it down. Okay, we will create a new one. So the result would be, if we do this 8C, the result would be one big one called employee. Okay, employee. Stay with me with my writing, all right? And within that employee, I will take F name, middle initial, L name, SSN, birth date, address, job type, everything. Actually, typing speed, T grade, and engineering type. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will have 10 attributes listed together here. All right. And then what I'll do next is that I will also have, I know that job type is the incriminating ones. So I will have, I'll do job type. Let me show you how it looks like. Subclass. Type. Wait. So I have this 10, and then I have this job type listed there, right? So I also have typing speed, T grade, engineering type. So what happened is that when there is a job type, let's say that this is an S, which is secretary, the typing speed will have some value in it. But when job type is like, for example, a T, technician or T grade will have some value in it. But when job type is an E, in engineering type will have some value in it. So this job type will be called the incriminating attribute. Do you know what I mean? Let me write. Okay, so the result. I have ไม่เห็น birthday address job I also have typing speed. Okay, so what happened when you combine the table is that now I have F name, for example, like they. Oh. Whatever the address. Now, if this person is an engineering type, then there would be some value in here, which is an engineering type A, let's say that. Now, I have the next person. But so job type is secretary. Then I have the typing speed, let's say 100. And the rest would be null.
So it's sort of like unionizing the relationship together in one database.
Yes. But then what would be the incriminating is this job typing, which is the most important thing, right? But what could be the key? The key will still be the, oh, SSN. Right? You make SSN key. And that's it. All right. This is number 8C. So 8C says that you create one. So 8C, what do we do in 8C? Let me go back to 8C. Is that this card is, I will fix the slide. Sorry about that. Then when you do 8C, is that you combine both super key, sorry, not super key, super class and subclasses together and form just one big relation. But you have to be mindful that when you do that, you probably will have to patch null value where it belongs. For example, right here, you have job type E, you have its engineering type, right? But if you have job type SS, you probably have the typing speed, and the rest would be null. You have to patch null when the value does not exist, right? Now, instead of doing this, if you do it the other way around, for example, in 8A here, you don't have null value, right? Because for this particular one, the differences would be this. For example, like secretary, you have this specific person with typing speed, but you don't have to keep T grade or engineering type for this person. So the spaces that you use within the database will be different. Which one use less space? Which one use less space? 8A, right? Because you don't have to patch so many nulls together. But if you have to join the table very often, then 8A would probably need more of the processing time, right? But if you do the 8C, it will be faster when you look for the information that may not have to be joined.
Does outer join all these super class and subclasses together? And whichever, like, let's say if the super class item has something that belongs to a particular subclass, then the other subclasses will have number.
Yes. Yeah. And now AD. So AD is the mapping of specialization using just, you say, single relation, but multiple type values. So the difference is this. If you take a look at the example here, I have part and I have overlapping, right? And then, so this part can be manufactured or maybe purchased part at the same time. So when I do this, what I can do is to create just one relation. So for this one relation, you have this part number and description that comes from the superclass, and the rest would come from subclass. Let's see, I have drawing number here. I have manufacture date here. I have batch number here. I have supplier name coming from here and list price here. But you will probably notice that, there is something different. You can see that these two particular attributes are extra ones that just happen here, right? So to do this, what happened is that you can say that if this part is manufacturer, M flag would be yes. If this part is purchase part, P flag would be yes. So if that happened, it means that you can either go to you can have the information for drawing number and manufacture date, and this is also true. But now if M flag is no, but P flag is yes, then this would be null, this would be null. If yes, then you have value in here. It's not the same because in 8C, what happened is that you only have, so 8C is actually good for, let me go back. So 8C is actually good for disjoint because you have one or the other. But then if you want to have like both, which is possible, then you have flag to signify whether this particular part number is actually both manufacturer part and purchase or either. So this is good for when you have the overlapping. All right. So you have to create two or many more of the flags to signify whether there might be information for this one. All right. So these are the 4 ways to map the specialization and generalization. A, B, C, D. Let me recap it again. For A, what you do is you maintain all superclass and all subclasses. But for subclasses, you take the primary key from the superclass in it. All right, 1, 2, 3 here. For 8B, what you do for 8B is that you do a subclass only. So you take each subclass, but each subclass would be each relation. So one relation for one subclass, another relation for another subclass, another relation for another subclass. But for each of the subclass, you must take all the attributes from its superclass. All right. For option number C, disregard this picture, but for option number C, you only have one big relation, which comes from both superclass and subclass. Okay, and that's it, like on the board there. And then for mapping of specialization of 8D, you have one single one, but you have flag for each of the type attributes, multiple type attributes, right? So there are A, B, C, D. Now, come to the next one. Almost done. I have just 3 more slides. Okay, now we're mapping of the what we call shared subclass, if you remember. For the example here, the shared subclass would be something. Let me see. Student assistant. Where is it? Here. Okay. Because it belongs to several classes, right? It belongs to employee, it belongs to student, right? So now for this chair subclass, it means that it has multiple inheritance. You have to inherit from, from every superclass. So you have to take the keys from their superclasses altogether. So you can see that in order to do this, you can use any of the options A, B, C, D before. So one of the ways that I'm showing you here is from 8A. So from 8A, it means that you take all of the entities and convert them into relations such that you get the person, which comes from here, employee from here, alumnus, okay, student, right? And then you take all of their keys, all of their attribute along with their key there. And then because SSN is from the of the superclass, you have to assign SSN into every of the class there. But now for the alumnus degree, you have SSN, have year, degree, and major all together. Where is it? Alumnus degree. Alumnus. Oh, alumnus degree with actually this comes from here. Okay. And then you have student here. Student here. So for student, you have your social student assistant flat, you have class, you have degree program, which came from the all of the attributes that belong to them, right? Oh, okay. Sorry. So this one is not 8A. So these we use 8C and 8D together. You can see that in order to do employee, let's take a look at the employee here. So employee, you have to take a look at this, its superclass as well. You can see that we use the 8D here because I have TA flag, RA flag to flag whether this employee is an RA or TA or not, right? Okay. And finally is the mapping of union types, all right? So union types, we have multiple, you have many category, you have many superclass, right? Okay, when you have many superclass, we will do something called surrogate key. So for this surrogate key, let's take a look at this. So we have the owner here. Okay. What we do is that we will create a relation owner to correspond to the owner category here. Right. And then we include any attributes of the category in this relation. So the primary key of owner relation is the surrogate key, which we call owner ID. But now we have to put owner ID and create this owns here. Okay. You can see that we do the owner ID and create this own, which comes from this one, and put the owner ID, which is a surrogate key, within this owns. So now we have, sorry? Oh, we created it. So it means that to map this, you have to create specify a new key attribute called a surrogate key. So a new one that you have to create. Right. You have to create it because by itself, when you say owner here, it doesn't have its own specific. Let me show you this. Okay. Because owner is actually the one that connects between the one who owns the vehicle, right? When you have the owner owns the vehicle, but owner has so many type of superclass, right? It has multiple superclass. And you take a look that each of the superclass has different key. So person has SSN, bank has B name. Actually, person has SSN and driver license number. And then company has C name, bank has B name. You cannot actually take just one of the key from their superclass, right? So because you cannot take any, just any of these, then you have to create a new one. That's the reason. So now you create a new one, meaning you create a key for this particular owner, which is the owner ID here. So this is called a surrogate key. You have a surrogate key because you cannot take just this or this or this key because they don't look like each other at all, right? Because it's multiple, it's multiple classes.
Find, say, the key from its superclasses.
Let's say that you have, let me write down.
Person.
Let's say bank ID. And then you have company, right? See company. Company as well. Now, if you have it in the same table, or you create a complete key. What happened is that you probably have SSN and this is null, right? But then you have an ID. This is null. You have company names, the rest would be null. So you cannot create the key this way because it cannot be a key, right? Because yes, yes. So the reason that you have to create a new surrogate key because you can't really combine the key like that. Okay, so that's it. Now we have all 9 steps all together, and that's the end. It's a lot. So let me go over the assignment a little bit. So there are 2 assignments. Assignment number 1 is something from the last 2 class. I give you scenario. For example, here you said that there's a company and company want to keep this department number, blah, blah, blah. You write ER diagram. And when you write ER diagram, you can use any tools at all. And usually I like E ER Win, or you can use oh, there are so many tools. You can use any tool to write your ER diagram. All right. But use Chen, CHEN Chen model that we do in class, and then use any tool to write it down. Now, for the second assignment, you click the file because I can't really put the drawing in here easily. So that would be 1, 2, 3, 4. I believe there are 4. I gave you 4 of the EI diagrams. And what you do is that from these ER diagram, you translate it to what we did today, which are relational models. So you have different relations and then all the foreign keys and everything connected to it. So yep, these are the 2 assignments. And then if you take a look at the due date, I put February 1st. So I gave you 2 weeks because next week you'll be presenting milestone number 1. So let me repeat again. For milestone number 1, we do not expect any database for milestone number 1 because you'll be focusing on your own project and the requirement, the solutions, and so and so. So the database part will not be concerned for this milestone number 1. But from this, I would like to encourage you to think about your project and comes up with entities. And then after you have the entities, you can draw their relationships all together. So then that would be presented during the milestone number 2. But right now that you are working on your SE class and think of the entities as well. So then you can complete your milestone quite easily if you think of the entity from now. All right. So is there any questions? Which Oh, I like ER Win. Actually, it was in the last 2 slide. I think that let me show you. Or was it in the second slide? I'm not sure. Or maybe second one. Should be this one then. Here. I put it in the last slide. You can take a look at it again. You can try different ones. I have the recommended database design tools, but ERD Plus is quite easy. Or diagrams.net, or I like these 3 that I circled. dbdiagram.io, but you can use anything at all. Or even if you are working on UML with the other class, you can use like Plan UML, but Plan UML doesn't give you the CHE and a Chen diagram. All right. All right, so I'll see you next week and looking forward to your presentation on milestone number 1. Okay, see you.
Clear with the difference between like super key. Could you provide more examples of in which super like as non-minimal super key, which cases will it be just the key as in a minimal super key?
Sure. Maybe what I'll do is I think I got many questions about that. I think I'll prepare like more details and more examples, and then of that, and address that, and also I'll put it, extra slides on it. Okay, thank you. Let me put this one first. And